Welcome to my new calculus site. I am John Gabriel. In this particular YouTube, I'm going to be discussing a very special definition by Euclid in the Elements. It's in Book 5 and it's definition 16. And it's a very important definition because since it was written, I'm convinced that no one except me has noticed the importance of that definition. And I'm going to show you how important it is in a little while. This particular YouTube video is about the integral, which is really a product of arithmetic means. It's not a sum, so you'll often see the integral being defined. Let me just connect my pen. Okay. So you'll often see the integral being defined as a sum. You'll see it being defined as a sum. I'll show you how now. So you really have Riemann's definition, which is, let's get a pen there, which is the sum of fxi times delta xi. Okay, so that would be the sum from I equals 0 to infinity, and this is just an approximation. It's never really the area of an integral or the volume, it's never really the area or the volume defined by the integral, because it's always an approximation. So this here is the Riemann definition. Okay, I'm going to show you that that definition is in fact wrong, and that the definite integral is really derived immediately from the mean value theorem. So if you take a look at the mean value theorem, it states this. Okay, and if we rewrite that as follows, this side here is equal to the integral from x to x plus w of f dash of x with respect to dx. Okay, and these two values here are arithmetic means, and I'm going to show you now in a very simple applet how those two values are arithmetic means. Okay, so let's go to the very first applet. Now, area is usually defined by modern academics as square units or triangular units, or in any particular way that you can think, which really boils down to a rectangular area. But the original definition by Euclid suggests a different definition of area and volume. But let's just stay with area for this particular presentation. What Euclid was telling us is that if we have a plane, let's imagine there's a line here too between these two green dots, in fact line like that, yeah, and if we have a plane that the sides are the numbers which are multiplied to give the area of the plane. But what does that really mean? Here's what it means. This side here is the average of all the vertical lines, right? So it doesn't matter how many vertical lines you have in there. If you take their average, it's always going to be 8.12. And if you move it up, you'll see that, again, it doesn't matter. Yeah? Same story. And you can see that if you look at the horizontal lines and you move, you add infinitely many horizontal lines, this 4.92 is always the average of the infinitely many horizontal lines. Does that make sense? Okay, so now if we add both the vertical and horizontal lines, we have a definition of the area in terms of the product of the two sides. Okay, the original Greek is very difficult to read. It's this definition here, And what it says is this. I'll read it in Greek and then I'll explain in English. Όταν δε δύο αριθμοί πολλαπλασιάντες αλληλούς ποιώσει τίνα, ο γενομένος επίπεδος καλείται πλευρέ δε αυτού οι πολλαπλασιάντες αλληλούς αριθμοί. Okay, that's ancient Greek, and it's really kind of difficult to understand because many of those words are not even similar to the modern Greek. Well, allelus, for example, is hardly used in modern Greek. It's ali, which means other, and there's no lus following it. And many of these terms, for example, genomenos, is also not a very commonly used. This word here, genomenos, is not a commonly used word in Greek. And of course, epipedos means level, and that's also similar to the modern Greek. Plevre means sides, and this big word that you see here, πολλαπλασιάντες, means when they're multiplied, and arithmi means the number, δύο means two numbers, όταν means if, okay, or when. Now, in English, the definition is this on the right-hand side. And when two numbers multiplying one another make some other number, then the number so created is called plane, and its sides are the numbers which multiply one another. If you really want to translate that properly, what you're really saying is that the sides, let's just do this over here, you're saying that the sides of a rectangular area, the product of the sides, let's call this A and B, what it's saying is that the product of the sides of a rectangular area is called a plane number. This is a plane number. And can you see that AB is the area? Does it have square units? No, it doesn't have square units. So according to the ancient Greek definition, area was not defined in terms of square units. In fact, it was defined in terms of rectangular or plane units. Okay, so this isn't really even a plane unit, it's just really the area described as a product of two arithmetic means. The infinitely many vertical lines is an arithmetic mean which gives us A, and the infinitely many horizontal lines is an arithmetic mean which gives us B. So if we come back to this now, we'll see over here that the average of these lines, the horizontal and the vertical, will give us the area of this whole rectangle that you see here. So it doesn't matter how we move it. Always the area, let's just cancel it, always the area will be the same, right? Doesn't matter which way we do it. Okay, so this is the first part of it. The second part I'd like to describe to you is really concerned directly with the area between a curve, as you see this red line, and the horizontal axis. So over here you see a particular line and the area is given as 20. That interval of 4 is the average of all the horizontal lines, and 5 is the average of all the vertical lines. Okay, and similarly, by the fundamental, or by the mean value theorem of calculus on this right hand side here, the horizontal line average or mean is 3. The vertical line average is 3 and the horizontal line average is 18, which is really just the interval width in both cases. So the area is always described in terms of these numbers, which are plane numbers. In other words, the natural average is the sum of all the vertical line lengths divided by the number of vertical lines. And we can show the quadrature in yellow. So if you had to do that, that means if you took the gray area over there, that particular gray area, and you squashed this triangular part down here, down, you'd end up with a plane number, which is 5 times 6. Similarly here, if you squashed this gray area down into this little dip here, you'd end up with a plane number, which is 3 times 6. Okay, 3 times 6. And so area is a natural average. Okay, it's the natural average of the vertical lines, or the y values, or the ordinates, multiplied by the interval width. And so this is how an integral is defined. This here is actually the mean value, and what this tells us here is that if you have a curve like this, that f dash of c is the arithmetic mean of all vertical lines. That's what that's telling you. F dash of c is the arithmetic mean of all vertical lines. I was the first in history to explain it this way. Nobody else even saw the connection. In fact, there was not even a rigorous proof of the mean value theorem until I came along. And I'll put a link to one of the documents, to one of the articles I wrote in which I prove it directly from the mean value theorem. And it's pretty easy to understand, because you can do it both ways. You can do it using the standard calculus with limits, or the new calculus, which does not use limit theory and is much easier to understand. And so that's pretty much what I wanted to talk about in terms of natural averages. Naturally, if you have a cube like that and you want to calculate the volume, then the integral in this case here, is a product of A, B, and C, okay? It's a product of A times B times C. And again, it's not defined like a Riemann integral. As a Riemann integral is defined, it's defined very differently. It's defined as a product. And in the new calculus, integrals are products of arithmetic means. Okay, so that's pretty much it for this presentation. I hope you've enjoyed it, and trust I'll be seeing you again next time. This is a new calculus. I'm John Gabriel.